So last week we had said that I would like us to discuss a little bit this table of ionization energies that is there in your book on page 35. And this table actually comes straight. Yeah, this table here comes straight from the book. I mean, I copied from there so that we have the same picture. And they give us the ionization energies for the first 11 elements up to sodium. Now let's see where the periods in the table here. Hydrogen and helium belong to the first period from the periodic table. So this is the first period. Then from lithium up to neon here is the second period. And just to get an idea of how these energies vary along a period. And then from sodium and beyond up to argon would be the third period, but we don't have values for that. They stop at sodium. It doesn't matter. So really we have two periods here, and especially the second period here that has quite a few elements, just to see if there is some pattern. What pattern do we see concerning the ionization energies? Now, the first column here, let's make it a bit. The first column, this column here, corresponds to values of the first, sorry, mistake, this column here corresponds to values of the first ionization energies. The first ionization energies, which means the energy required to remove the first electron from each of these elements, of the atoms of these elements. Yeah? So we see from hydrogen, we need 1,310 energy joules. Goodness, does it say what values are these? Sorry, let me check something. And it doesn't, but we assume that these are joules of energy needed to remove one electron from the hydrogen atom. Well, it's only electron that it has. It does not have any more. Whereas we need 2,370 joules of energy to remove the first electron from the helium atom, and so on. Now, if we go to in the second period, from lithium up to neon, look at this. Overall, if we look at these values, they begin from 519 and end up to 2,080 joules. Overall, the values of the energy that is needed to remove the first electron of the atoms of these elements increases along the period from left to right. I mean, if we look in the periodic table here, I have the periodic table here underneath, we are talking about this period from lithium up to neon. We see that the energy overall increases. We need more and more energy as we go from left to right to remove one electron from atoms of these elements. I don't know, does it fit if we have both values in the periodic table? Yes. So from lithium, beryllium, boron, you see that lithium, beryllium, boron, carbon, and so on, up to neon. Overall, the energy increases to remove the first electron, although there are some anomalies here and there. There are two anomalies, and it's better to see these anomalies in the form of a graph rather than in a table. I have a graph here that we can use. So you see from the values from lithium up to neon, which is the second period, overall increase, but there are some anomalies. You see between beryllium and boron, and also between nitrogen and oxygen. Instead, I mean, the energy that we need to remove one electron from boron is less than the energy we need to remove the first electron from beryllium. And the same happens here. And we're going to discuss reasons why. But overall, we see that we need more and more energy to remove electrons as we go from lithium to neon. That is, as we move along the period from left to right. And here are the energy kilojoules per mole that is necessary to remove these electrons. You see these values that in the table in the book supposed to be kilojoules, isn't it? Yeah, kilojoules per mole, yeah. Now, why does it say kilojoules per mole and not just kilojoules? Let us discuss that. So these values are actually kilojoules per mole. Why? Because in order for us to compare these ionization energies that we need to supply to remove the first electron from these atoms, in order to make it a fair comparison, a fair test, the samples that we use are atomic samples. That means 1 mole of atoms of each of these elements in the gaseous phase, So in order for us, in other words, to measure how much energy is needed to remove one electron, the first electron from these atoms, we use 1 mole of atoms in gaseous phase. So an atomic gas, in other words, we use atomic gas, 1 mole of atomic gas of each and every element here in standard conditions. And then we can, the value of energy that we use to remove 1 electron is these values here, and then we can compare them properly. So that is why these energies here represent kilojoules per mole. I mean, the energy that we have to supply our sample, 1 mole of sample, to remove the first electron. So anyway, so that's a small parenthesis now to discuss the units of these energies that we need. Now, to remove the first electron from each of these atoms, we call it the first ionization energy, and it has the symbol of 1. This little I means ionization, the 1 means the first ionization energy. Similarly, to remove the second electron from these atoms, we would call it the second ionization energy, and we would give it the symbol with a 2 there, means second, and so on. The hydrogen has only 1 electron, of course, so only the first ionization energy has meaning here. The helium can have 2 ionization energy, to remove the first electron, the first ionization energy, and the second ionization energy. And as we go down, we have more and more ionization energies. And these numbers here, 2, 3, 4, and so on, represent the subsequent ionization energies that necessary to remove further and further electrons, always of 1 mole of atoms or ions. In other words, these are, if this energy is necessary to remove the first electron from helium, then what we are going to be left with, we are going to be left with a positive ion. Then this energy here will be the energy necessary to remove the second electron from this ion that is left after removing the first electron. Okay, so all this from the second ionization energy and beyond, we're talking about energy necessary to remove an electron from the remaining ions from previous removals of electrons. Always talking about 1 mole of atoms or ions in gaseous phase. Anyway, so let us look now whether we see any other pattern here. If we look, let's see something with more than 1 ionization energy. Let's start from lithium, for example. We see to remove the first electron, we need to supply 519 joules per mole. To remove the second one, we need to supply 7,300, which is a big gap. I mean, a big jump from 500 to 7,000 and so on, and then 11,000 and so on. So here we see a very big gap. Let's see further down. From 900, we go to 1,760, then we go to 14,850. So Although these two numbers are kind of relatively close to one another, but then from there to there, there's a big gap again, from 1,700 to 14,000, nearly 15,000. And if we go further down now, for boron, 599 for the first electron, 2,000, about 2,500 for the second, then about 3,6 for the third. And then from 3,500, suddenly a huge jump again, 25,000. We see what a big jump of energies is from this nearly 4,000 to 25,000. And further down, as we go along, we are going to see more of these jumps. Look at this, from 6,000 to 37,000. And here again, another huge jump, and another here. So now I'm going without looking at the numbers, because look at the pattern. Diagonally going down, we see these huge gaps as they appear. And of course, the last one from 29,000 to 141,000, humongous jump. Obviously, there is a reason why suddenly, although we need kind of comparable number of joules to remove some electrons, and suddenly we need a huge, to supply a very big difference of energy, a much bigger energy suddenly. Now these jumps, as you can understand, I'm sure you can figure it out by now why we have these big jumps, is because to start removing from these electrons to go to the third electron, obviously this third electron belongs to a different energy level, as you can see. And let us see, for example, here at the beginning where we have atoms with few electrons and it's easy to draw them. Helium, for example. Let's start with helium. Here I have a little picture of helium. Helium has 2 electrons in its first energy level, and this energy level is complete now. So to remove one, we need 2,370 kilojoules of energy per mole. To remove the second one, we need 5,000 and so on. Now, if we go to lithium, well, after that, of course, there are no more electrons. So there's no change in energy level of helium. That is why we don't have any big jumps of energy. I mean, the 2,500 and 5,000 are relatively close, nearby numbers. There's nothing strange about that. Now, in the case of lithium now, though, the lithium has 2 electrons in its inner energy level, which is complete, and 1 electron all by itself in the second energy level. So this electron here, which is the first electron to be removed, needs relatively a small energy, 519 kilojoules per mole. Is enough to remove this extra electron. But then the remaining electrons now are in the inner, in the energy level number 1. And that is why to remove now the second energy, to the second electron, we need kind of quite a lot of energy, extra energy to remove it. That is why we have a big jump from the 500 to the 7,000 kilojoules. And these electrons now, these two electrons in the inner energy shell, obviously we can understand why they need more energy to be removed, because they are closer to the nucleus and they are attracted quite strongly with electrostatic force, because the nucleus, remember, is a positively charged item in the atom, and attracts the electrons with the electrostatic force. And of course, the closer the electrons are to the nucleus, the more strongly they experience this attraction. And that makes sense. It makes a lot of sense, that is, that we need more energy relatively to the first energy that we needed to remove the first electron from the second energy level. Similarly for beryllium here, the first electron, now let us figure out the electronic structure of beryllium. It has 2 electrons in the inner energy level, which is corresponds to n equals 1. And the other 2 electrons are in the energy level number 2. So these first 2 numbers correspond to energies required to remove these 2 electrons from energy level n with the quantum number n equals 2. So 900 for the first one, 1760 for the second electron. But then, once this energy level has been emptied, the next electrons are from an inner energy level with n equals 1. And they need more energy to be removed because they are closer to the nucleus. And that is why we see a jump from the 1,700 to 14, nearly 15,000. So from nearly 2,000, we go suddenly to 15,000 energy, which is a big jump. And the reason being, again, is because we change now energy level. So we see now all this energy, the big energy jumps that we see along each row here in the table correspond to change in energy level. We got to inner energy levels here, and that is why the energy required suddenly increases manifold. So this is one indication that indeed the electrons surrounding or orbiting around the nucleus do belong in particular energy levels, and each energy level has a range of energies which are distinguishable from other energy levels. So this is an indication of the structure of an atom in in fact the electron configuration around the nucleus, that it belongs to that the electrons belong to different energy levels. So it's an evidence of the electronic structure. And now let us see an example relating to this second period in the periodic table, from lithium up to neon, and see if we can discuss why there are some inconsistencies in the energy, the first ionization energy necessary to remove electrons, like from beryllium, between beryllium and boron, and between nitrogen and oxygen. Why this discrepancy here, this abnormality? Why these two do not follow the general rule, which is to increase the first ionization energy? Now, but before we start this, I want us I want you to see if there is any problem here up to what we were discussing. In general terms about this table. Okay, good. All right, so let us share again. All right. Here in my notes, I see another one. Let's go back to this table. There's another big jump from there to there. You can see it from 494 kilojoules per mole to 4,000, 4,500. There's another big jump. And of course, we can see why there's a big jump, because this electron here of sodium belongs to the third energy level, and it's all alone here, so it's easy to remove it. But after that, after this first electron, the other electrons now, these electrons here belong to the energy level with n equals 2. That is why they need a different energy, a different range of energies. Up to, we remove them, all of them, until we get to this jump again, which means that up to this about 30,000 kilojoules, actually the electrons is energy to remove all of these electrons from energy level 2. And then we go to the first energy level, and we need even more energies. Anyway, that is, sorry about this parenthesis. Now let us go to our task, which is this one. Let's read what we need to do in this problem. It says, one of the trends in the periodic table is that the first ionization energy increases from left to right across a period. Yet the graph below shows that boron has a lower ionization energy than beryllium. So we need to discuss this discrepancy here. Why boron has less ionization energy than beryllium? And when we say ionization energy, we talk about the first ionization energy. Yeah. Why this discrepancy? So let us see now. We have some questions to answer here. So we're going to concentrate on these elements, which are elements of the second period in the periodic table, from left to right, from lithium to neon. Complete an orbital diagram for each element, beryllium and boron. They only want us to complete the the orbital diagrams for beryllium and boron. Let us make this a bit smaller. I have, like the beryllium and boron, just to remind you that beryllium has 4 electrons and boron has 5 electrons, okay? And as we see, the energy level equals 2 for beryllium, has 2 electrons, whereas in boron, it has 3 electrons. It's the next one in the main groups of the periodic table. So this has 3 electrons, this energy level, and this has 2. Now let us see, when they say they want us to draw the orbital diagrams, they mean this, remember when we draw how the orbitals, they want us to draw the electronic configuration of beryllium and boron in the orbitals, to place this electrons into orbitals. Here I have the beginning of the energies of the orbitals, because beryllium and boron have very few electrons, so we only need the first few energy levels. So for beryllium that has 4 electrons, the first 2 will complete the first energy level, which is the 1s, then we go to the 2s, then the 2p, then we don't have anything for the 3s, but nevertheless. Okay, 2 electrons plus another 2 is 4, and this is the electronic configuration of the beryllium. It only has 4 electrons. So how else can we write this electronic configuration? We can write it as 1s2 and also 2s2, which means 2 plus 2 is 4 altogether. Now for boron, again, we can start from the first energy level, the lowest energy level, takes up the 2 electrons and it's complete. Then we go to the next energy level with another 2 electrons. 2 plus 2 is 4 electrons. Now we have an extra electron there, which will go to the 2p. Here is the 2p, the 2s, and the 1s. Remember, as we go up, the energy of these subshells increases, and this is how the order in which we fill them. So here we have the difference between beryllium and boron, and how can we write this in this form? 1s with 2 electrons complete, then the 2s is also completed with 2 electrons, then we go in the 2p level and there is only 1 electron. Here is for boron and this is for beryllium. 2 different forms of showing the electron configuration of the 2. And okay, so these are the orbital diagrams that we're asked to complete. We've done it. Complete an orbital diagram for each element, beryllium and boron. Then they ask us to write the electronic configuration for each, which we have done it already. We wrote the electronic configuration for each. This is for the boron, sorry, and the other one for, sorry, what am I saying? This is for beryllium, beryllium, and this is for boron. The electronic configurations, as they asked. Next, they ask, using these electronic configurations, explain why boron has less ionization energy than beryllium. Okay. Explain why boron has less ionization energy than beryllium. And in fact, if we want to see the table for beryllium and boron, let's see how much is the, where is this table? What's the table? The beryllium and boron, the first ionization energies. These are the 2 ones that we are interested. For beryllium is 900, for boron is about 800. So beryllium 900. So for this is 900, and this is about 800, like 799 if I remember correctly. These are kilojoules per mole. And they say why this is less than that. And now that we have the electron configuration, we can use either this notation or this notation, which is perhaps it's easier, the one that shows the orbitals. We see that the boron has its last electron, although it's also in the second energy level, but it's the first electron, actually the one electron, is in a higher energy level. I mean, it's in a subshell of the second energy level, but the p subshell has slightly more energy than the 2s level. That is why it's a little bit higher, and that is why the 2s levels complete first before the p orbitals, isn't it? So this one has a little bit higher energy, the electron of this in this orbital, and which means it is so much easier to remove this electron than an electron from the 2s orbital, which, look at this 2s orbital of the beryllium. It has its 2 electrons, which makes it quite stable because it's its last this last orbital is complete with a pair of electrons. This is quite stable, and it takes more energy to remove one of these 2 electrons that form a pair than this single electron from the 2p orbital. And so it makes sense that this can be removed a lot easier than this one. And that is why this energy, this ionization energy, is less than the energy required to remove one of these electrons here, the 900. Always when we have orbitals which are fully, in fact, we're going to see an example in the same period of the, so maybe I should stop talking and we'll discuss it when we get there. Between the nitrogen and the oxygen, we see the same trend here, the same abnormality like we see with beryllium and boron. We're going to see there again the same story and why it's the second one can be removed much easier than in the first, the previous element. So anyway, here I hope that you understand that this electron here by itself in this energy level to be, which is further away from the ground state, it needs less energy to remove this lone electron than this electron from this complete orbital here. And let's go to our problem. Using this electronic, it says, using these electronic configurations, explain why boron has less ionization energy than beryllium. So boron has less ionization energy than beryllium simply because it is easier to remove one electron from the boron than the beryllium, which has a more stable structure with its complete orbital that has a pair of electrons in there. It was a 2s orbital, if you remember. Okay. Which other case, it says, which other case seems to be similar in the same period? Well, obviously the same. Another case that seems to be similar is between nitrogen and oxygen. Let us discuss about, they don't ask us to discuss it, but let us discuss why. And in order for us to discuss it, let's also draw the electronic configurations and the orbitals and draw the orbitals of these 2, nitrogen and oxygen, and see what is the problem. Okay. Before we go to the nitrogen and oxygen, let us also see something else here. I just want you to understand that, look at the boron and look at its orbital diagram. You see that this 2p, one of these electrons, like it's on its own, some in a higher kind of energy level, like the 2p. This is how it's shown in the picture here. These two together belong to the same 2s orbital, a pair together. So it's a lot more difficult to unpair a pair of electrons. Anyway, let us go to the nitrogen and oxygen. Here is the orbital diagrams for the nitrogen and the oxygen. The nitrogen is before the oxygen in the periodic table. It has 7 electrons or 7 protons, and the oxygen has 8. I mean, this is the number of protons here, just the atomic numbers, 7 and 8. Okay, so for nitrogen, so its first 2 electrons are in the energy level number 1. Then it has, in the second energy level, it will have 2 2, 4, 5. Isn't it? It's 7 electrons together. Okay, this is for nitrogen. Now for oxygen, it has 1 extra electron, so it's the same shape really, but with an extra electron is the nucleus, and we have 2, 4, 6 plus 2, 8. It's 8 electrons altogether. All right, something like that we can represent it. And here we have how we can place them in their orbitals, you know, the orbital diagram that we are so familiar with, which is this one. Let us do them in these orbital diagrams as well. It's actually the same thing here, the same representation here. It's just that they show them all in one page.